Hi folks, so welcome back to another lesson, and we're going to look at nuclear reactions in more detail now. And particularly we're going to look at something called nuclear fission and describe it using equations, and also carry out calculation involving mass loss and the energy released in a nuclear reaction. So definitely more physics than the previous lesson basically. So first of all, nuclear fission involves a nucleus splitting into two large fragments, and you may remember this from Nat 5. So isotopes can spontaneously fission, and remember that means it can happen without any reason, it just happens when it does. However, most need to be induced, so try and use this new word here, induced, and it's done so by absorbing another particle, usually a neutron. So the isotopes most used in nuclear reactors are uranium-235 and plutonium-239. So that's a wee bit of background knowledge that you're expected to know. Now, when the radioactive isotopes undergo nuclear fission, they give out small particles which change their mass a little bit and their atomic number slightly. And you now know how that happens because you know that you can get either alpha, okay, decay, and how that changes the mass and atomic number. You know that we can get beta radiation, which again can change its atomic number. And you know that gamma radiation doesn't change its atomic or mass number at all, but it does give out energy. Now, how do we know if a reaction is induced or spontaneous? Well, to do that, we have to look at the actual equation. So here we've got an equation down here. And if there's a neutron present on the left-hand side, that means there's an induced fission. And if there's no neutron present, it's a spontaneous one. So that's the bit that we're looking for on the left-hand side there. So you can see there is a neutron there, so that means it must be an induced fission. So for me, the key bit there to write down is this bit there. I don't know what's happened to the red border. So fission of uranium-235. So we have a uranium atom and a fast neutron. And if the fast neutron goes towards uranium, do you think any fission will happen? The answer is actually no. Fast neutrons will generally just pass through the uranium nucleus without causing it to split. What we need to do actually is to use a slow neutron. And the reason for that is because the slow neutron is going to be absorbed by the uranium nucleus, which makes it unstable and increases the chances of it actually splitting into smaller nuclei. And in the process, 3 fast neutrons are released. So the key point here I want to take a note of is that to induce fission, we have to use slow moving neutrons. So what happens if we have this reaction? Well, quite often it can lead to something called a chain reaction. And remember, a chain reaction is where we trigger the reaction and it releases more reactants, if you like, that can then spread the reaction on and on. So for example, if you think back what we talked about there, 1 neutron can cause a uranium atom to split, releasing 3 more neutrons. So then 3 more uranium atoms can be split, which then leads to 9 and then 27, and it's an exponential growth. So in a nuclear reactor, this is what's likely to happen. And the way we control that is by using something called a carbon moderator, which actually slows down the neutrons so that they can either collide and trigger more reactions, or if they slow down enough, they don't collide and trigger reaction. And all of this energy is released as kinetic energy, which leads to a resultant rise in temperature. So to control the chain reaction, as we said, we use carbon rods called moderators. So if it's a controlled reaction, it's a nuclear power station. And if it's an uncontrolled reaction, we have a nuclear bomb. And that's the basic idea of how to build a nuclear bomb. Now, when a nucleus undergoes fission, the products that are made, so the resulting elements that are made, are completely random. So what we mean by that is you could have one reaction where you get barium and krypton and 3 neutrons released. You could do the exact same reaction and get lanthanum, bromine, bromine and neutron release. I think this is lanthanum release. And notice how you have the exact same reactants, but the products are totally different. And you can't predict which products are going to be produced in a nuclear reaction. Okay, the key thing, however, is that some of the mass is missing. Although you might say, well, why is it then that these numbers here have to be conserved, i.e. the same as the number on the left-hand side? And the reason is because the mass is lost so small, we can kind of just assume that these still stay the same. So the products have a mass which is about 0.088% less than the reactants. So this is why we can say these numbers are still conserved, but actually that's not really true. Now this change in mass is called the mass defect. I need to know this word, and you also need to know the definition of it. So copy this definition down. Mass defect is the difference in mass that is equivalent to the binding energy that holds an element together. So that binding energy is the energy that holds the elements, all the protons and neutrons together. The difference in energy, or the energy created, is converted into kinetic energy of the reactant particles. On a large scale, this appears as heat. And this is why we can use nuclear reactions as bombs or as a way to generate electrical energy. Now, how do we get this energy from matter? And this is where Einstein came up with probably his most famous equation. Okay, the amount of energy produced from the mass defect M is given by Einstein's famous equation. E is equal to mc squared. And c in this case is the speed of light. Now, to give you an example of how much energy could be produced, if 1 kilogram of uranium atoms were all split, then there would be about 0.88 grams of mass missing. This could be converted into 82 trillion joules, which is enough to run a 2-bar electric fire for about 1,300 years. Obviously, we're assuming all of the atoms are split and all of the energy released is being used. That doesn't usually happen. Now, a quick point about this equation. A very big misnomer is people say that because of this equation, energy and matter are the same thing or the equivalent thing. That's not really true. So how do we use this equation? Well, let's look at a worked example. So we've been given a radioactive decay here, and we're asked to balance the equation, explain how this is a fission reaction, is this a spontaneous or induced reaction, and finally, given the following, calculate the energy released. So we never expect you to remember the masses of these particles. You'll always be given a table of data which you can then use. Now, the only thing to note here is that the mass defect is always given by the initial mass minus the final mass. So this is the one time where we do an initial minus a final to find the difference. And the reason for that is because, remember, our reactants lose mass, which is converted into energy. So let's look at how to do each of these questions in turn. So the first one, to balance the equation, I hope you can do that because it's simply adding your numbers on the right-hand side and making sure they're equal to the left-hand side. The one trick to this equation, though, is notice there are 3 neutrons, so you've got to multiply that 1 by 3. So the answer for this one is 91 and 56. And to check it's correct, remember, if you add the sum of these, they must equal to the sum of these. And if you add the sum of these, they must equal to the sum of these. Remember, the mass and proton numbers are conserved, must look to the same on either side of the arrow. Explain how this is a fission reaction. Well, first of all, it's a fission reaction because the reactants break down into elements with smaller mass, because we've got one element here and we've got 2 elements there. Is this a spontaneous or induced reaction? Well, remember, we're looking at the left-hand side, and if there's a neutron there, it's generally an induced reaction. And there's the answer there and the explanation. Now, the final bit is the bit that's got the calculation. So, given the following, find the energy release. So what we do, first of all, is the left-hand side, and we have 1 uranium and 1 neutron, so it's simply these two added together. Now, a wee point, these calculations are fairly simple in that you're just adding things and using Einstein's equation. However, they can be difficult because you've got a lot of these numbers here and they're all raised to a power. So when you enter this into your calculator, be very careful to make sure you're typing in the right numbers. I would actually do the calculation twice so that you double check it and you don't make a silly calculation error, because this is where people usually make the mistake. Again, don't round your answer until you get to the very end. So I'm leaving my answer there as it is, and then I'm going to do the right hand side. So the right hand side, notice we've got 3 neutrons, so that's why I've got to multiply the mass of the neutron by 3. Again, do the calculation twice just to check you've done it correctly. And we're almost there. We find the mass defect by the initial mass minus the final mass, which gives us this. And then we plug it into our equation, remembering it's the speed of light squared, and then we round and actually include the units. So the answer there is 2.8 times 10 to the 8 joules of energy are released. And the final thing to remember is that despite this loss in mass, your nuclear equations must still balance, i.e. the sum of the left-hand side must equal to the sum of the right-hand side. And that's how you do E is equal to mc squared calculations.